Now I'm going to show how continuous time differential equation can be used to model protein degradation. Previously, I mentioned that no calculus is required for this course. Actually, the reason I'm showing you this equation is to show how this is related to the differential equation that we've been using so far. So let me start with this graph. T on the horizontal axis, this is time, and we have Y, protein concentration. So initial concentration is here, and there's no production, so protein concentration decreases like this, exponential decay, right? One thing we notice is that when Y value is high, here, when Y is high, our slope is very steep. And if Y is not so high, for example here, then we see that our slope is not so steep. This is something we observe, right? And the question is, how can we model this using continuous time equation this time? So the equation that we use is called the differential equation, and it is like this. dy dt is equal to negative dy. And this d is a real number. So d is real number, and it is greater than 0. Basically, this equation is telling us that because we have a negative sign here, how fast y is decreasing, the rate at which it is decreasing is proportional to y. This equation is basically telling us that if this y is large, then the rate at which y decreases is large. And if y is small, like here, then the slope, this value, the rate is small. Basically, that's what it's saying. And this negative sign, again, indicates that the rate is a decreasing rate, not increasing rate. Now, I want to show you how this is related to differential equation. So now we have this equation, dy dt is equal to negative large D times y. Now the question we have is, what is this dy dt when time is t1? So I have this point t1. Let's see, this is t1. And my question is, what is this slope here? This slope at this point. And one way of approaching this problem is using an approximation. We pick another point close to t1, then we say this is t2, and we find the slope between these 2 points. Basically, we draw a straight line between these 2 points, and then we find the slope, and then we say that slope is close to the slope that we are trying to find out. So let me magnify this part. So here we will have t2, and here we will have t1. This is y2, and this will be y1. Now, what is this slope then? This slope can be approximated like this. Delta y over delta t, which is y2 minus y1 over t2 minus t1. We just say the time interval is just 1. Then this will be same as y2 minus y1. And again, delta t is 1. So it's 1 minute, 1 hour, whatever it is. We are assuming that it is just 1. If you go back to this equation and plug that slope into that equation, this is what we have. y2 minus y1 is equal to minus dy1. Why y1? Because we are interested at time t1, right? We are interested in time t1. And at that point, our y value is y1. So we have y1 here. Now, let me rearrange this equation a little bit. So we have y2 plus y1. We just move this term to the right. And we have minus dy1, which is equal to 1 minus d times y1. Let me convert this into another form. So instead of saying y2 and y1, we say this one is previous value of y using the discrete time index I, and this is current value of y. Then what do we have here? We have y of I is equal to 1 minus d y I minus 1, right? And if you call this p sub y, then we have the difference equation that we had before. So we see that this py is equivalent to 1 minus d from this expression. And also we can see that if this large d is large, let's say 0.8, then our py becomes 0.2, right? Small. So if there is more degradation, the p sub y value will be small. And if d is small, like 0.1, p sub y value will be 0.9. So if there is less degradation, then our p sub y value will be high. So we see the relationship between p sub y and d in this slide.